Everyone's going to have a different answer.
Yeah, like, well, that's obviously can't tell if I cut the thing.
Print everything out.
Check. Sure.
I just don't feel like trying to deploy the work environment and problem crashes that work in other environments.
Another kind of
Okay. Good morning, everyone. It's time to start. So first of all, I got a very important appointment on Thursday, which I cannot reschedule for family. So I have to cancel the lecture on this Thursday. I apologize for that. And I will make an announcement. I will make an announcement on campus later. That means Thursday we don't have a lecture. Okay. But you guys might have more time to do the homework while it is due on this Friday. So if you haven't yet started, please do it right now. Otherwise, you don't have enough time. I guarantee about that. Okay. Today we're going to talk about a new topic. It's called linear models, which contains a set of learning algorithms for this specific type machine learning models called linear models. Well, by looking at the words linear, you might think, okay, it's simple. Yeah, the definition of linear models is indeed simple, but how to learn that and how to extend it to nonlinear models are very, very important. Plus, even linear models sound simple, is still widely used in real world. And we're going to use these fundamental models to explain the many, many important ideas in design training algorithms or in generalizing well. Later we'll see that the well-known support-back machines are essentially based on linear classifiers. And of course, later we have some like beautiful trick. It's called the kernel methods to extend SVM support-back machines to nonlinear models. But essential, I mean, the whole idea, the key idea is still based on linear classifier notations and settings. Okay? So before we proceed, this is a checkpoint. Look at the bigger picture. We haven't seen so far. So we have introduced supervised learning, right? The most commonly used learning framework, where we have to define the instance space, the label space, and hypothesis space, right? So the hypothesis space is essentially the family of the function candidates we're gonna learn from. So as we discussed previously, learning is essentially a searching procedure. You're gonna search over a family of functions and find one you believe is best and is closest to the ground truth. Right? So that's the essence of a learning procedure. And how do we conduct supervised learning? We prepare a set of label data, right? Typically, it's pairs of instances and their labels. And then we feed this data into some learning algorithm, right? In other words, you can will this data is kind of a guide the search of the learning algorithm over the hypothesis space. After the learning is done, you locate a particular hypothesis as your learned hypothesis. We expect this learned hypothesis or model H is close enough to the ground truth. Right? That's the whole framework. And once we have obtained our learned hypothesis, we can use it to predict the label for new examples. And inside this framework, we have seen quite a few learners, right? Decision trees, our very first learning algorithm, ID3, right? And then we talk about ensemble learning. And basically, you're gonna find a smart way to assemble a set of existent classifiers into a more powerful one, right? Two common strategies. One is called boosting. The other is called bagging, right? And boosting tries to ensemble a set of weak classifiers into a much stronger one. While bagging does not require your classifier to be weak. You can use very strong classifiers. And bagging just take their average. Why? Because this can improve the robustness, reduce the variances. That's what we discussed in the last lecture, the bias and variance decomposition. And the random forest, right? I'm using random trees to reduce the correlation between the hypothesis learned for each iteration, and so on. And also we have discussed the several general concepts like feature augmentation as high-dimensional vectors, and the concept of overfitting, right? And why should we avoid overfitting? Because in practical applications, the data are often corrupted by some noises. Right? If you fit the trained data too well, it's likely that those noises can mislead the learning procedure and end up with a hypothesis which does not generalize well. Right? But I mean, there's an exception. It's called data boost. Right? We have seen in the last lecture that data boost, even the overfit to the trained data, it seems those noises doesn't affect its generalization performance. But this is just one exception. You will see in numerous models and algorithms, they overfit the trained data, they end up with bad results, including neural networks. And we also introduced several theoretical concepts in computational learning theory, right? What is path learnability? Probability, approximate correctness, right? So we need to know why we should use probability, right? Because the training data are essentially random. Right? You draw training data from an unknown data distribution. You don't know the quality. You cannot guarantee the quality of the training data is always good, right? One training set might be good, the other might be wrong, right? So you cannot guarantee. You cannot give 100% guarantee of the learning performance because it is dependent on the data. That's why when we define a good learner, a bad learner, we just require that, okay, if you have a large chance to give me a good hypothesis, that's okay. Don't expect that you give me 100% guarantee that blah blah blah. That's not feasible. Okay, So these are kind of like a very quick overview of the big picture we have seen so far. Any question? Okay. Yeah, hopefully that this will quickly refresh our mind, right? And connect all what we have discussed so far, so that you're not gonna be lost in some specific models and algorithms. Although we're gonna look at those algorithms one by one, but we cannot forget their connections. We want to merge them together in a very organized way. Okay, so we're gonna first introduce the definition of linear classifiers. So you will see that we can define a type of classifier, but we might have like 100 learning algorithms to learn that. So we'll first give the definition of linear classifiers, and then we'll talk about the expressiveness of linear classifiers, and we'll compare its expressiveness with say decision trees, those models we have just discussed. Okay? And then we'll start with linear regression model first. Why? Because this is the easiest one, and I think many of you have taken statistics class before, so you should be familiar with linear regression. And here we chose the most commonly used techniques to learn linear regression model, which is called least square method, from which you will know that how do we design the objective function or cost function, and if you want to optimize it, how do you conduct a gradient descent framework or stochastic gradient descent framework, which these kind of frameworks are widely used in modern machine learning algorithms. Okay. So first, what are linear classifiers? We're going to give some kind of formal definition. Then we'll introduce the geometry of linear classifiers. One elegant property of linear classifiers is that they have a very intuitive geometric illustration. And we'll use that geometric illustration throughout this semester, and talk about the motivation for a set of algorithms. So this is very important. But of course, you need to recall some kind of knowledge you have learned before, maybe in high school. Like how do you use an algebraic way to represent a hyperplane, a boundary, a line in two-dimensional space, three-dimensional space, or high-dimensional space, right? So, and then we give some notational simplification. I mean, just for ease of notation, nothing else. But don't confuse those notations. Okay. So, before we introduce the definition, let us look at some concrete example first. So suppose we are given this data set, right? Blue circles and red triangles, which will you can view them as negative examples and positive examples. Now, this is your training set, and we want to learn a classifier which can well fit the training set. In other words, we want to find a classifier which can well separate those blue circles from those red triangles. Right? So if you design a classifier, which kind of classifier you feel is good? Any thought? Yeah, just a guess.
Draw a line.
Draw a line?
That goes roughly between where the triangles and circles mix, and then on one side of the line is circles, and the other side is triangles.
Yeah, that's our linear classifier, right? But before that, what is the intuitive way to separate those blue circles and red triangles? Any thought? Yeah, that's one line. That's one method, right? But here, I mean, I want to use a more straightforward way, right? For example, I just run and draw a curve. I can draw a curve. And I can use this curve to perfectly separate every blue circle from red triangles, right? And suppose this is your learned classifier. This is their decision boundary. What's the training error? It's simply 0, right? Yeah, it's simply 0. The training error is simply 0. Of course, another way, as you guys just pointed out, right? I just go straight to the answer. We just draw a line. Right? We just draw a rough line, which kind of like roughly separate these two types of examples. So now there is a question, right? I have a wavy line, a beautiful curve, which can well separate, perfectly separate all the positive examples and negative examples. I got a rigid line, which can only roughly separate positive and negative examples. So there is a problem of model choice. So which one do you believe is better? Or if you the designer, right? You are the user. Which model would you like to choose? Any thought?
Well, I imagine the curve is probably more prone to overfitting. So I probably would just want the line.
Because the line is less prone to overfitting, right?
Yeah.
Okay. Any other additional comments?
A curve would be harder to make than a line. Like, you know, because if the line has a gradient, it goes through, but like a curve, it separates. It changes at every peak and at the value and at the far. It changes. There's no set for the curve.
You mean the gradient of the curve is too complex?
Yeah. I think that coding that would be hard, right? Like just,
Oh yeah. That's an interesting point. Actually, we are talking about how to implement this linear classifier or non-linear classifier, right?
Right.
Okay. That's an interesting point. Yeah. In addition to what you have pointed out, right? Let's just assume, okay, coding is feasible. But the problem is, as you just mentioned, overfitting issue. Why? Because this curve is too kind of like sensitive. Right? And it's very easy to be changed if some examples are mislabeled, right? Or corrupted by some noises. For example, imagine that the curve, this red triangle here, is supposed to be a red circle, a blue circle, negative example. But due to some noises, it was corrupted. The label was flipped to the red triangle. That's why the curve here has such a large curvature. And then the problem is that, okay, next time if I test on a new example here, right? And the ground truth is blue, but because this curve is kind of distorted due to the noisy label, the curve can only predict this as positive, namely the red triangle. Right? And on the other hand, if you take a look at here, right? So because surrounding those red triangles, or most red triangles, right? Only one exception here. Right? It's likely that, okay, this blue circle is just a noisy label. Its original label should be, say, the red triangle. But to fit every training example, right, the blue curve here has to make a big bending. Right? And so when you do the testing, suppose near this region, you got a new example whose ground truth label is red triangle. But now the blue curve, this curve can only predict it as a blue circle. Why? Because this is the decision boundary. All the examples on the left hand side of this boundary is predicted as a blue circle. On the other side, it's predicted as a red triangle. But now let us look at the line. The line is pretty robust, right? So you can see that, okay, the line misfits this red triangle here, and also misfits this blue circle here. But there is a reason, right? Because this red triangle and this blue circle are likely to be noises. So if you choose a appropriate line here, if you can avoid being affected by those noisy labels, so that we will see new test example, we can give correct prediction. Like for this blue circle, because it stays on the left-hand side of this dashed boundary, right? So it is predicted as correct, and also this red triangle stayed on the right of this boundary on line B, right? So it is predicted as a red triangle. So it's much less influenced by the noise labels, which kind of like perturbated in the boundary. So for the case, let me point out that here and here. Right? So you can imagine how linear classifiers. You can see that intuitively how linear classifiers are more robust as compared with those more refined but delicate classifiers, which are very sensitive to the data, right? And similar argument can be made for the regression test. Suppose these are the training points, right? So the feature is just one-dimensional x, right? And the y-axis indicates the label, which is continuous. This is regression test, right? If I want to perfectly fit this training data, how should I do that? Take a curve, right? And go through every point. And this can be easily done by high-order polynomials. If you have taken class before, it's very easy. You can construct a polynomial which can fit as many points as you want. Right? But what is the problem? The problem is still the overfitting, right? So imagine that I'm just using a line to fit these data points, right? Of course, I cannot make this line pass through every point. Right? You can see kind of perturbation surrounding the line. But the benefit is that this line will be much robust to a noises. Right? Take a look at here. Right? This point is very likely the value of the output value is corrupted by some noises, so it is stretched here. And if you use a very delicate, very complex models, well, it can perfectly fit this point, but the consequence is that, okay, this whole curve, you can see that it's stretched and bended here. But actually, when you have a new test example, it's likely to be here. Right? This is a bar choice. And now, if you use this curve A to make prediction, you can see that this error is large. However, if you just simply use a line, it can resist most of those noises, and the prediction error is much smaller. So this is a value of linear models. So although it seems simple, right, it doesn't give you perfect training error, but it can avoid being affected by noises in a large degree. Right? Avoid overfitting, in other words. So now let us look at the definition of linear classifiers. So we assume, in general, the infant is an n-dimensional vector x, and output label is either -1 or 1. Someone asked why don't we use 0, 1? They are the same. If you use 0, 1, and when we talk about a few things, we need to make some kind of transformation, but the result is exactly the same. Okay? So let us just, for simplicity, require that our output label is either -1 or 1. Okay? So linear classifiers are also called linear threshold units. So this term, or this jargon, comes from the neural network literature. So they will linear classifiers as the simplest neural network. That's why they call it linear threshold units. And why it is called threshold units, we're going to discuss about later when we talk about neural networks. Okay, so let us first call it, right? Just call it. So linear threshold units classify a particular example X using two parameters. One is a vector, it's called B vector W, and the other is a bias parameter B, which is just a number. It's a scalar. It's not a vector. And according to the following classification rule. What is the rule? We're going to first compute a classification function or decision function. Right? This is simply W transpose X plus B. In a product between the weight vector and the feature vector plus a bias term B. Then we just look at the sign. If the sign is 1, you give the prediction 1. If the sign is negative, you predict the label as negative. That's it. And B is called bias. Any question?
What is sign? What is that function? What is that function?
Oh, sign, just look at the sign. If you're a non-negative number, the sign is just 1. If you're a negative number, the sign is minus 1. That's it. Any other question regarding the definition? Okay, I'm sorry I have to mainly use pointer to this screen because it is recorded. We cannot simultaneously record two screens. But I will occasionally point here. Okay, so this is the definition of linear classifier, right? Oh, by the way, this is just a definition. But the training essentially is to obtain the estimate of weight vector W and B. So you'll have a variety of ways to estimate them from data. So that's why there are many linear classifiers, which we're going to look at one by one. Mm-hmm.
How do we select the bias?
Yeah, that's a good question. This is the training algorithm. This is how training algorithm does that, and we're going to discuss in detail algorithm like perceptron, like support vector machines, like logistic regression, and so on. Okay. So linear classifier has a nice geometry. It's very intuitive. Why? So you can imagine. Okay, let us assume we have these two sets of examples, positive and negative. Right? And the classification rule itself essentially defines a classification boundary. What is the classification boundary? Any thought?
It's a line.
Yeah, it's a line. How do we represent that line? Right? Algebraically, what is the neutral? What is the neutral region for the classification?
The segment of what quadrant, that's the neutral area, right? Which are not classified yet.
This one?
Yeah, that quadrant and that quadrant.
Yeah, you're right. I mean, we need to express it in terms of formula, in terms of mathematical expression. So remember, for any example, right, given a classifier, we just look at the value of this classification function, right? If this function is bigger than or equal to 0, we assign a positive label. If it is less than 0, we assign a negative number. So the neutral region or the neutral case happens when this classification function value is simply 0. So if you represent this case by this equality, right, the classification function value is equal to 0, geometrically, it corresponds to a line. Right? This is what we have learned in our high school math, right? Or first year college. I can't recall, but anyway, everybody knows that this represents a line, right? And we know that on one side, all the examples on one side will have this classification function to be positive, right? On the other side, we'll have this classification function to be negative. So this line actually separates all the positive examples from all the negative examples. That's why we call it a classification boundary. Right? And if we draw a line or vector which is orthogonal to this classification boundary, how do we represent this orthogonal vector? Let's just try to recall what we have learned before. What's the representation of this orthogonal vector? Any thought? It is the weight vector. It is W1, W2. Well, of course, we need to put them together. It's a weight vector. Why? Right. Okay. Let us take a basic, very brief review. Right. So imagine 2 points on this classification boundary. Right. So any point in this classification boundary is satisfy this equality. Right. So if we take 2 points here, if you from these 2 points you can draw another vector, right, which is parallel in this boundary. So and you got. Let me write it down in Blackboard. Maybe that will be better. So this is the classification boundary, right? So suppose all the negative examples here, all the positive example here, right? And we know this boundary is mathematically represented by a equality, which are W transpose X plus B equals to 0, right? Here I did not expand W1, W2, blah, blah, blah. I just represented as an inner product between vectors. And now, we want to know how do we represent this orthogonal vector, orthogonal or perpendicular to this boundary, right? So to do that, let us take up any 2 points in this boundary, right? Which we denote by, say, x1, x2, right? I put the 2 on the bottom to indicate this vector, this feature vector, right? So we know that those x1, x2 stay on the line. Both of them satisfy this equality, right? So let us just write it down. So we know that W transpose x1 delta plus b is 0, right? Because x1 stays on this line, must satisfy this equality. And W transpose x2 plus b equals to 0, right? These 2 facts. Now what we do is just subtract the left-hand side, the first one, by the left-hand side of the second. So then what we can get is x1 delta subtracted by x2 delta equals to 0 because b here is cancelled, right? So now what can we observe? So first, what does this mean? What does this mean?
That's the vector pointing from x2 to x1.
Yes, exactly, right? That's how we represent a vector vector starting from x1 pointing to x2, right? So of course this vector is on this hyperplane, on this classification boundary, right? And what about this? In geometry, we know that if two vectors are orthogonal, their inner product is simply 0, right? So this is W. This is W. So because for arbitrary 2 points on this classification hyperplane, we know that W will transpose their difference, meaning the vector on this boundary, their inner product is W simply 0. So we know that W is orthogonal to the whole boundary. So this is some review of actually we have learned before. So let us go back. Yeah. So here just to give you a basic facts. So all the the orthogonal vector to this decision boundary is simply the bit vector. And another thing we need to be aware is that because we're doing classification, we only take we're only care about the sign. That is the value. If this classification function's value is bigger than 0 or less than 0. So we don't care about the skew. That means you can multiply all those parameters by an arbitrary positive skew. It doesn't change the position of the classification boundary. It doesn't change classifier at all. You can multiply WB by 0.001 or by 10 to the minus 6 or 10 to the 10 to 6 by 1 trillion. It doesn't change the classifier at all. And this view can be generalized to like n-dimensional space, right? In n-dimensional space, an equality, a linear equality here represents a hyperplane, which why we call hyperplane is n-dimensional space. And the hyperplane will separate the whole space into two half spaces, here and here. So this is a geometry view of linear classifier. Any question? Okay, great. So we see that to identify a linear classifier, we need to know two parameters: the weight vector W and bias parameter B, right? But sometimes if you just explicitly writing down them, it feels kind of annoying. Right? I don't want to write two parameters together, and we want to simplify the notation. How can we do that? We can augment the feature vector with a constant 1. We insert this 1 in front of x, right? We denote the new feature vector by x prime. Same time, we can fold this bias parameter into the bit vector. So you got a new bit vector W prime. Right? So then you increase the input dimension, and correspondingly you add one more parameter, which is bias, into the bit vector. You can represent this classification function by the inner product between the new bit vector and new feature vector only. Right? W prime transpose x prime. And then look at the sign. So in this way, we do not need to explicitly write down the bias term B. So sometimes we're going to just use this. But just to be aware, the bias term is still there. It has a different meaning from the V vector. So we're going to discuss later. Any question? Okay, great. So coming up in the next several weeks, we're going to talk about a series of linear classifiers. We're going to start with the classical algorithm of perception. You see that it is kind of error-driven learning mechanism or online learning mechanism. Just look at the examples sequentially. one by one, and use the current model to make prediction. If it makes wrong prediction, it adjusts the weights and bias parameter and try to correct its mistakes. Otherwise, it just remain the current status. It's kind of lazy learning. Okay? And this is called perception. And then we will look at this classical and very powerful linear classifier called support machines. So see that the essential trick is to define a different cost function that not only includes the error term in fitting the training data, but also a extra term that targets the future performance, which actually bounds the generalization error. So this type of approach is called structure risk minimization. And then when we talk about probabilistic learning or Bayesian learning, we'll introduce two actual linear classifiers. One is called naive Bayes classifier. So it's a simple linear classifier, but with elegant probabilistic interpretation. And then we'll introduce logistic regression, which is another popular probabilistic linear classifier, and which is mainly used for like online advertisement recommendation systems, like in Amazon. But no matter how those algorithms estimate model parameters, they all gonna follow the same way to make prediction. That is, look at the classification function value and look at sign. If it's positive or non-negative, you give a label positive 1. Otherwise, you give label -1. Okay. And here, I just want to point out there is another set of linear models, which is called linear regression. And the task, instead of doing binary classification, is regression, meaning you're going to predict continuous values, like what is the temperature tomorrow, what is stock price tomorrow, right? And linear classification is about predicting a discrete label. Okay, so now we have finished the introduction of linear classifiers. So next, before we proceed to detailed learning algorithm, let us first look at the expressiveness of linear classifiers. What kind of functions do linear classifiers represent? So we're going to introduce several examples in the family of Bloom functions. We'll see that actually linear classifiers are expressive, but not as expressive as decision trees. So we'll use the Bloom function as an example. What is Bloom function? The inputs are all binary, and output is binary as well. So we can view them as true and false or 1 and 0, right? Whichever is fine. So we see that many Bloom functions are linearly separable, not all though. And but we know that decision trees can represent any Bloom functions. So decision tree is typical, is the typical nonlinear classifier. Okay, we're going to first introduce the example linear classifiers. Can be linearly classified. These are called conjunctions and disjunctions. It's very commonly used Bloom function. So let us look at this simple conjunction function, which is a conjunction of 3 Bloom variables, x1, x2, and 3. So here, this table includes all the inputs and the function values. Right? So we know that only when all 3 input variables are 1, the conjunction is 1. Otherwise, it's simply 0. Right? So now the question is that how can we say this conjunction function can be perfectly represented by a linear classifier? Any thought? Think about the rule, right? Think about the rule of the conjunction. So we know that this conjunction is equivalent to like y is 1 if and only if all 3 variables are 1, meaning that the summation of all 3 variables are no less than 3, right? remember, x1, x2, and 3 are either 1 or 0, right? So if you want all three variables to be 1, you need to, you can express it as their summation to be less than 3, right? So in this way, we can see that when you move these 3 to the left-hand side, you got a classification function, x1 plus x2 plus x3 minus 3, and we just look at the sign. So if it is negative, meaning that at least one variable is 0 or false. So you got left-hand side, you got this one to be negative, right? And then your classification result is simply 0, which is consistent with the ground truth function value, right? And only when all x1, x2, x3 are 1, this value is 0. And according to our rule, we're going to classify this example as positive, which is consistent with the ground truth. So now we have created an equivalent linear classifier to this conjunction. Okay. Now we can make it a little bit complicated, right? How about we put some impose some negation before doing the conjunction? Can we find a linear classifier that perfectly represents this function? How can we do that?
Just flip the plus to a minus.
Yes, exactly right. Remember, negation is simply flip the value, right? In terms of mathematical expression, you can represent it as 1 minus x3, right? So that basically is saying, okay, this y is 1 if and only if x1, x2, and 1 minus x3 are 1, right? So x1, x2, and 1 minus x3 are 1. That basically means their summation must be less than 3, right? So now if you just move this 3 to the left-hand side, you got your own, we can move 1 to the right-hand side anyway. You can get your new prediction rule, right? x1 plus x2 minus 3, and subtracted by 2 is non-negative, right? And correspondingly, we can construct a linear classifier. So what is the weight vector for this equivalent linear classifier? Any thought? Following definition.
Just one negative one.
Yes, exactly right. Remember our definition is W transpose X plus B, right? So of course X now expanded X1, X2, and 3, right? W1, W2, and W3 are coefficients of those X values, right? So you can just look at the coefficients, 1, 1, minus 1, right? Or 1, 1, negative 1. And bias is minus 2, right? Because we assume it's plus B, right? So you move it here, you move 2 to the left-hand side, you got minus 2. Any question? Okay, great. So now I leave this exercise for you. What would the linear threshold function be if the conjunctions here were replaced with disjunctions? So suppose our y function is a disjunction of x1, x2, and x3. How do you represent it as a linear classifier? This will be an exercise. You just follow the same strategy. Okay. Any questions so far? Great. So a second set of linear functions, or that can be perfectly represented by linear functions called M of n functions. So what does M of n function mean, right? So we're assuming we have n variables in total, and y is true if and only if at least m of them are true. So suppose you got three Bloom variables, x1, x2, x3. Now my 2 of 3 rule, or 2 of 3 function, just saying this function is 1 if at least 2 from these 3 variables are true. Right? Like for example, x1 plus x2, x1 and x2 are true, then function is true. x2, x3 are true, function is true. Or x1, x3 true, function is true. But if there's only one variable, which is true, and then the function is still 0. Now I want to ask, how do you represent this M of n rules as a linear classifier? Any thought? No idea?
I guess we would have to use disjunctions, right? To represent it.
It's unnecessary. You can just come out. You don't need to reuse our previous result.
Could you just let LU be 1, 1, 1, and then just let E be -n?
Yes. Yes. Right. So you just follow the rule, right? We require that at least 2 of those variables to be true. Right? That means if you add them together, their sum should be no less than 2, right? And in general, if it's M of n, you just write it as x1 plus x2 plus x3 plus blah 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 plus xn is no less than m. Right? So it's a seemingly complex function, but when you represent as a linear function, it's very succinct, very succinct and compact. Yeah. Question? Okay. Right now, I want to introduce a set of functions which are not linearly separable. So when you're training examples x-based kind of parity, it is knowing that, it is proven that those examples are not linearly separable. So, for example, if you have like 2-dimensional feature vectors, right? Here are all your positive examples. Here are all your negative examples. And you can try your best to draw a line. You can try all kinds of lines. You'll find that you can't draw a line to separate these two classes, no matter how you place them. This actually exacerbates the weakness of linear classifiers, right? So a typical Bloom function, which has the parity, is called XOR. So XOR function, you will see that you will never be able to find a linear classifier to separate positive examples and negative examples. So if you represent XOR function, it's like that, right? So remember, x1, x2. XOR means they have to choose different values to be 1, right? Either x1 is 1, x2 is 0, or x1 is 0, x2 is 1. Right? In that case, you cannot find a linear classifier, a line to separate those positive examples from negative. In general, if you have if the numbers of y's is even, and it exacerbates parity and cannot have any equivalent linear classifier. So XOR is maybe the simplest function that cannot be linearly classified, and there are many non-trivial Bloom functions, and like 4 variables here, and you can show that this function is not linear in the 4 variables as well. So this is actually I want to share with you some history. So the invention of the perceptron in the last century, like 1950s, like triggered kind of evolution. People found this might implement artificial intelligence, those ambitious goals. And then later, the Minsky is a pioneer in artificial intelligence from MIT. They show that perceptron, which is typical linear classifier, even cannot recognize XOR function. So that is the reason that leads to the depression of artificial intelligence. If you know artificial intelligence, we know that we have went through like 3 depressions. Right now is the resurgence again. Yeah, that's the second depression. And later people find okay, we got many beautiful tricks like kernel trick, like nonlinear classifiers, like neural network can overcome this problem. So they kind of revive. Okay. Now let us discuss the several simple strategy, a simple strategy to get over this issue, to get over this parity issue. So we know that. Take a look at this example. So those points are all staying in one-dimensional space, meaning that they just stay on the x-axis. Positive, and on 2 sides are negative. So we know that we cannot find any line which can separate all the positive examples from negative examples. There's no linear classification boundary. And how can we deal with that? We still want to use linear classifiers. A trick is to change the representation. Now that in the original feature space, I cannot find a good line to separate them. Why not we just augment the features? And now I want to represent each data point in a 2-dimensional space. So the first feature is the same as the original feature, just x. But the second feature, I just take the square of x. So remember, this doesn't, use new information. This is just based upon the existing feature values. I just create some kind of transformation based upon the existing features. So I expand or augment features. So each point can be represented in a higher dimensional space. And what will happen if we do this feature augmentation? If we look at the distribution of these positive examples, negative examples in a new feature space, you'll find that now it looks like positive and negative examples are linearly separable. Okay. So that's the power, right? Actually, this is a key strategy. We actually add one more dimension of the feature, which by taking square of the original feature value, and now you can well separate previous examples. So in general, this idea is called feature mapping and kernel trick. You will see that with the kernel trick, you are able to extend many linear classifiers to nonlinear classifiers. And the extension is pretty easy and straightforward, except for like support vector machines. If you want to do the extension, you need to look at the dual space of the solution and do a kind of like mathematical derivation. But other than that, it's really straightforward. Okay, so I'm gonna leave you guys exercise. How would you use the feature transformation idea to make XOR in a 2-dimensional space, so that all examples through XOR will be separable in this new space. So this will be our homework. In homework, I think homework 3 or homework 4, I guess. Yeah. Here is the thing, right? To answer this question, you need to think about a function that maps examples from 2-dimensional space to a higher dimensional space. So through what kind of new feature you can separate those positive examples, negative examples. You might think of like using x squared. It might not work, but it might be like x minus x squared or whatever, x cubic. Okay, any questions so far? we're gonna revisit this idea again, because it's a fundamental trick. Okay. In our previous discussion, we always want the data set, the training examples are linearly separable. Right? But in most cases, I mean, in real world, you'll find that it's very hard. Right? You can not guarantee those examples can be perfectly separated by a line or hyperplane. So we're gonna make some compromise. Assume that we're able to almost linearly separate the data set. So this is called almost linear separable data. And to find such a line, we need to consider how much noise do we allow for. And we know that there must be some training error here. Right? So actually, the supervised machines, their advanced version that called soft SVM, essentially is making such kind of trade-off. Okay, so far we have discussed the expressiveness of linear classifier, right? So we know that many functions, for example, in Bloom function family, are linear, and it is also a good guess for hypothesis space, meaning that okay, if you are given a research problem which you believe machine learning can work, which classifier would you like to use first? Linear classifier. So every time I'm going to first try a linear classifier and to see if it can give you reasonable good results. And if it is not, then that means okay, machine learning method might not be good. Your data quality is problematic. And then if you want to further improve upon the linear classifier, you consider more complicated methods like complex machines, like neural networks, and so on. So in practice, it is also a good guess for the hypothesis space, but we should be aware some functions are not linear, typically XOR functions, and other trivial Bloom functions. But we got a trick to get over this. There are ways of making them linear in a higher dimensional feature space. This trick is called feature mapping or feature transformation. Okay, any questions so far? Great. So the last thing we want to discuss about is why should we add a bias term? It seems kind of like excessive, right? Why should we add a bias term? Why not we just use W transpose X equals to 0? Or in other words, W1X1 plus W2X2 is 0. Why?
Without the bias, it forces it to go through the origin, and that might not be where your data is.
Yes, exactly, right? Bias actually allows you to move from up and down, right? If you don't have a bias, well, your classification boundary will always go across the origin, right? That actually restricts your flexibility. So if we take a look at this example, so all the positive examples here are kind of surrounding origin, right? All the negative examples here. If you get rid of the bias term, you're gonna have misclassify many positive examples, right? Whatever W you choose. Only when you have a bias term, you can move them like downward a little bit so that you can perfectly separate the positive and negative examples. So that's the usage of the bias term. So don't think it's annoying. It's useful. It's actually increase the flexibility. Okay, so now we have finished the introduction of the linear models, and go through the very first linear model learning algorithm. It's called least square method for linear regression. Okay, so what we have discussed was the definition of linear classifiers, what the expressiveness of linear classifiers, and then we'll proceed to linear regression first. It's kind of odd because we're going to spend quite a few lectures concentrated on different linear classifier learning algorithms. So we're going to first talk about the linear regression because it's kind of isolated, and then we'll spend most time on linear classifiers. So we're talking about least square method for regression. We'll start with some examples, and we'll propose the so-called least mean square objective, which can be viewed as the cost function. And we'll talk about how to optimize this function to get the parameters. We know that the linear models have two parameters, the bit vector and the bias parameter. Okay? So we're going to talk about the gradient descent framework. Perhaps many of you have used them before. And then we'll talk about stochastic gradient descent framework. And sorry, stochastic gradient descent framework is actually even more robust and more widely used in modern machine learning tasks, especially for deep neural nets. Okay. So here is our example. Suppose we want to predict the mileage of a car from its weight and age. And suppose we have collected a bunch of data sets, data points, right? So car 1, you got its weight, x1 is 31.5 times 100 pounds, right? Of course, the car cannot be 31.5 pounds, right? And you have driven for 6 years, and the mileage is 21. I guess it's 21,000 miles. No, it's not possible. 21,000 miles for 6 years. It's not possible. Maybe 220, 210,000 miles. And you have a second car whose weight is 62.2 times 100 pounds, 2 years, and miles like 250k miles possible, and the other 2 points. So now, from this data set, what we want is I want to learn a function that can predict the mileage using any x1, x2. That's our problem formation, right? So you're given this task. I want to train a model to make such a prediction. Then what I first need to define the model, right? So here we're going to use linear regression. We assume that the output is a linear function of the inputs. In other words, we assume the mileage is simply a bias term plus W1 x1 plus W2 x2. So here, for convenience, we just denote the bias term by W0, right? Or you can view it as the notation simplification tree, right? We add a constant feature 1, and the corresponding weight W0 is essentially the bias term. And then, what is the learning? The learning essentially is to use the training data to find the best possible value of W. If we collect all the parameters W0, W1, W2, right? This is a vector, right? Denoted by this bold data W. Right? We use the training data to find the best possible value of this bit vector W. Then after the learning phase is done, we want to make a prediction. How can we make it? Given the value for x1 and x2 for a new car, and use the learned bit vector W to predict the mileage for this new car. That's it. So this is how typically a linear regression model is formulated. Okay, here's the framework. In general, for linear regression, in general, we assume that inputs are vectors from like D-dimensional space. We assume, okay, each input is represented represented by D features, right? And outputs are just real numbers. And we have a set of training data denoted as pairs of x1, y1, x2, y2 to say xm, ym. And we want to approximate y as a linear function of all the feature values in x. So namely, y equals to w1 plus w2 x2 plus plus wd xd. Right? Remember, we have a d features in total. To simplify the notation, we're going to represent it as an inner product between w and x. And here we use the notation simplification trick where we add a constant feature, right? 1 here, and the corresponding bias term is w1. So you got w1 times 1 plus w2 times x2 plus w3 times x3 until wd times xd. You got w inner product is x. So for simplicity, we'll always assume that x is 1. So the feature is augmented. Right? Feature is augmented like that: 1, x2, x3 to xd. Well, this is a d-dimensional space, essentially the augmented feature space. So if we want to insist on the original definition, well, your input space will be d minus 1. But now you add one more feature, constant, in order to absorb the bias term. So your feature space now becomes d-dimensional. Any questions so far? Everyone's comfortable? All right, okay. So a few concrete examples, right? So in a one-dimensional input, so that means you have only one variable x1, x2, you have y, and we're going to predict y using this rule. This is a linear model, right? w1 plus w2 times x2. And two-dimensional input, x2 and x3, of course, you need to augment feature 1 so that the feature vector will be in three-dimensional space, right? So w1 plus w2 x2 plus w3 x3, right? w1 here serves as a bias term, right? So those red points indicate the position of the training points, right? And if you want to learn a linear regression, essentially to find a plane, right, which is as close to these points as possible. And maybe there are many points just stay on the plane, but it's really unlikely. So there are always those points like up and down, but still close to this plane. Okay, so now we know the model formulation, right? We know the idea. The question is, how do we know which weight vector is the best one for the training set? If we look at the example, right, we just have discussed, right, that is equivalent to asking, right, how do we find a position for a line, right? Why don't I make the line like that or like that? Right? How do I move this plane, right? Adjust this angle to make it to be close to the points, as close as possible. How do we do that? Any thoughts? If you view it as a learning procedure, you can imagine that, okay, your teacher has given you some example, right? And try to learn it, and if you learn well, you can make a good prediction. You're gonna have some kind of reward, right? Otherwise, you're gonna have some penalty. You're gonna have some cost. So now I want you.
So to find the best one, would we do similar things to before through like the previous learning algorithms where we minimize error?
Yes, exactly right. Yeah. we need to define some kind of error. Or in this topic, we really refer to as cost. So you're trying to adjust your hyperplane, your line, right? The position, the angle, such that if you make a wrong prediction, you have to suffer from some cost. And you just look at how much total cost using your classifier to make prediction. I want to minimize this cost. By minimizing this cost, I found the best position of the line or the hyperplane. That's the key idea. So what's the cost? For a particular example, a very commonly chosen cost is just simply the absolute difference between the training label, the ground truth, and your predictions. So of course, I want this cost to be as small as possible. And in general, we have many data points, right? We might have 1,000 data points or 10,000 data points, and we just add up all the cost functions, and then take the square. We define this objective function as the cost function or loss function. So in the future, you will see many terms like cost and loss. They're actually saying the same thing. So, and we take the square of this difference, and then add that over all the training examples and put a constant 1/2 in front of it. We define this as our cost function on the training set. Then our goal is to minimize this cost. I don't want my classifier to make more mistakes, to incur more cost or penalty. And then the problem becomes an optimization problem. I want to find a best bit vector W to make this cost function as small as possible. Someone asked, why do we take a square here? The reason is simple. Because it is easy to compute. Nothing else. Well, you can use this as well, but you'll find that to optimize this is much less convenient than you take a square. But just be aware, if you take a square over this actually amplify large errors, right? If your prediction for a particular example is large, and then your cost is double. It's not double, it's squared. And then you incur much more penalty. So this cost favors you to make, or prefer you to make many small errors, but does not allow you to make large errors. This might not be good for some specific applications, so people will switch to other loss functions. Okay, I think we can stop a little bit early today, and because we continue to proceed, there will be many details pop up. Okay, again, I apologize. I have to cancel the lecture on this Thursday. I'll make the announcement on the